understand why periodic trends are important, we need to look at the periodic table to begin with. We need to understand where we came from, what was developed early on, and where we're at now. So the first question I have for you is, why would we care about these trends? Why do we need to know and understand these properties that we observe throughout the periodic table? What use could that be? Well, let's think from a practical standpoint. Let's say I am an industrial chemist, not even a research chemist that just gets to indulge, my whims, but I'm an industrial chemist. And I have profits that I need to make and shareholders that I need to appease because people have invested money into my brain and what my brain can produce. All right. Well, as I'm trying to develop something, and even in academic research, this is still the case because you have grants and everything. As I'm trying to develop something, do I just like toss things at the wall and hope they stick? Or do I need to come up with a methodology that makes sense? Do I need to have a body of knowledge that I can fall back on in order to come up with something that's a logical proposal? I absolutely need the logical proposal. Now, I mean, every once in a while, yes, sometimes science is dirty and it's messy and we do throw things at the wall to see what sticks. That does happen sometimes, but most of what we do does come from a basis of, all right, here we have this problem that we need to solve. And when we think about the scientific method and we think about a hypothesis, all right, a hypothesis is a guess. So it can be that down and dirty, throw things against the wall and see what sticks. But typically speaking, as scientists, we accept a hypothesis to be an educated guess. The key word there being educated, where we look at that body of knowledge and we draw upon that. And so when we look at the periodic table, if we're trying to predict things, if we're trying to understand how things interact with each other, if we understand that within the periodic table, there are a lot of patterns that exist, there's a lot of predictability there, we can use that as a basis to start that groundwork, that foundation for figuring out, all right, I have problem X. I need to begin at step Y. Now, the periodic table we have today, it's evolved. When we go back to how the periodic table was eventually created, we have to go back to a man named Mendeleev. Now, okay, so I want to caution you to understand something. Textbooks credit the people that were ultimately given, the discovery credit. But back then, in the days that scientists like Mendeleev were working, the internet didn't exist. This global society that we have wasn't a thing. And so oftentimes there was a problem and a lot of people were working on that problem. And it could be that, it took forever for people to communicate with each other. And so it was really whoever managed to get to like the reporting bodies first or disseminate their information to everybody first got the credit for it. And a lot of times other people worked on it. These days, if you pull a research paper, you're oftentimes going to see a slew of authors on there. All right. When I finished grad school and I had moved on to other things, I still occasionally got pinged that I was given an author credit to something because the lab that I worked in as a master's student was still doing research based on work that I had done as a student. And because I had done some of the groundwork, my PI still gave me credit as one of the co-authors because I'd done that groundwork study. Back then, people didn't do that. It was all glory for the one person that did the discovery. So Mendeleev, I want to mention, was not the only one that was working on this. He's just the one that managed to get it out there first. And he did a really good job. I don't want to discredit his work. All right. Mendeleev did a really good job. Because when I look at Mendeleev's periodic table, okay, he put things together a little different than we have now. He did things by atomic mass. And he was able to, based on blank spaces, figure out what some missing pieces were. So he looked at things like gallium and germanium. He was able to predict their approximate mass. He was able to predict, things like, well, did they have a low or high melting point? Did they have a low or high density? Back then, things were done with classic wet chemistry. So they would form oxides, they would form hydrides, they would form chlorides, they would form compounds like that. And so he was able to predict properties. Okay, so Mendeleev took the 65 known elements at that time and he arranged them by atomic mass. He arranged them by recurrence of physical properties, and he got families of elements with these similar properties that allowed him to predict those properties of unknown elements. Did a pretty good job. When you think about the fact that they did not have the modern techniques that we have today, and he was able to predict what he predicted, it's pretty remarkable. So when I look at the periodic table, this was Mendeleev's original periodic table. Now things were a little different. Mendeleev was not an American, all right? And so they oftentimes would superscript things instead of subscript things like we do today. So when you look at the formulas of the oxides and stuff like that on here, you'll see a superscript. The hydrides, you'll see a superscript. Okay, a couple of blank pages here that he was able to predict the properties of. He knew there was something at about mass 68. He knew there was something at about mass 72. He just didn't know what they were, but he was able to predict their properties. Now, there's things on here today that don't exist, like we don't have an element J, which is a bummer because my name starts with a J and that'd be really cool, right? But it did a pretty good job, okay? So this periodic table was also called the table of periodic law. All right, so periodic law was what was being used at the time that this was developed. So what is periodic law? All right, so periodic law says when arranged by mass, the elements exhibit a periodic recurrence. I can spell recurrence. That's better, recurrence of similar properties. Okay. All right, so that's periodic law. Now, what we have today, though, is a little different. We don't do by atomic mass. So think about what you learned in your prep chem class. How do we arrange the periodic table today? We arrange it by atomic number, which is the number of protons. Okay, so we've since refined our periodic table to be arranged by atomic number versus mass, which is much more useful for predicting elemental behavior. And so our periodic table today, it is similar to this, but it's a little bit different because now we go by atomic number. So today, number, not okay. So we're arranged by atomic number. And remember, the atomic number is the number of protons. All right, and so here is the way our periodic table looks today. Now, you'll notice down here, the image that I used to have in these slides was from early 2000s. Okay, I've replaced it with a more current one. These guys were not all filled in with the image that I used to have. We've done a lot of advances to filling in the end of the periodic table since then. Now, a lot of things in the periodic table now are anything that we've added in. These are things that we have created in particle accelerators. They don't last very long, and it takes a long time for them to be proven and then to be put on the periodic table. All right, so when I look at my periodic table, I have my periods. Now, each period is where we start another energy level. Okay, so period 1, we only have energy level 1, n equals 1. Period 2, Okay, now we have n equals 1 and n equals 2. Period 3, now we've added in n equals 3. All right, so we're adding new energy levels each time that we put a period in. When I look at my groups though, when I look at my vertical columns, this is where we start to match things up based upon those trends that we see in the periodic table, because now we're matching up with atomic number. You know, we know that our groups have similarities to them. One of the big similarities is that, especially in our main group elements, all right, let me put this main group here, our group tells us the number of valence electrons. Okay, you'll notice that there's group 1 through 18, or we have group 1A, 2A, and then a bunch of B's in the transition metals, and then we go back to the A's when we, hit the main groups again. The number before the A for the main group elements is the number of valence electrons. All right, so number before the A in main group elements is the atomic number. I mean, is not the atomic number, is the number of valence electrons. I'm thinking atomic number too much. Is the number of valence electrons. So group 1A, I have 1. Group 2A, 2. Okay, I go over to group 3A. And so on and so forth. And why is that important? Well, that predicts a lot of the behavior that we see, because the valence electrons, those are the outermost electrons. So they're the most accessible. They're on that outer shell. Those are the ones we can get to the easiest. And so because of that, all right, if I have one valence electron, I see a lot of similar behavior, because that one valence electron is going to pop off pretty easily, all right? Now, how easily it pops off depends on how far away from the nucleus it is. So something like potassium is going to pop off its valence electron easier than lithium, because potassium is in period 4, so the valence electron is super far away, is shielded by all the other electrons in the center, and so it comes off a lot easier. Lithium, that valence electron's a lot closer to the nucleus, so it's held on a little stronger. All right? And so we've got that similar behavior. When I get to group 4A, now I have 4 valence electrons, and so I'm kind of in between. Do I take off 4? Do I add in 4? But then when I get over to group 5A with nitrogen, it's a lot easier to add in 3 than it is to take off 5. All right, and so that's what we have with our periodic table today. And so it's really important to understand what we're seeing with this periodic table and understand how everything goes together to help us make some of those predictions and understand some of the behavior that we're going to see. Even when we start adding stuff in with particle accelerators, here's what's really interesting. So I started college in 1999. So it was a long time ago that, at least according to the periodic table, that I started studying this stuff. And we didn't have names for elements 113 through 118. In fact, I'm pretty certain that we didn't even have like a particle accelerator version of like 109 on there yet. It's been a while since I've looked at a periodic table from when I started college. And what was really interesting is that as I studied chemistry longer and we started to get these man-created elements to hang out around a little bit longer, what got filled in was 108, 110, 112, 114, 116, 118, the even numbers. And I remember my second semester general chemistry class going up to the professor and asking her, well, is there something about that even number there that lends itself to more stability? Because we hadn't even gotten out to 118. It was really just like 106, 108, and again, maybe 110. I can't remember now if 110 was on there when I asked this question or not. And they were placeholders. They were like these UU things. They didn't have official names yet. But even back then, like that trend, that pattern stuck out to me. that the ones that we could get to stay stable longer, long enough to start putting on the periodic table, had even numbers. And if you go back to a periodic table even from 15 years ago, you will see the placeholders are there for the even numbered ones. And it's only been very recently that we've been able to add in the odd numbered ones. And so there's a trend there. There's a behavior there. There's a pattern that we can use as, we make more discoveries or come up with more experiments or things to check out. All right, so that is an overview of why we care about this before we start delving more into the nitty-gritty here on the periodic table.